Perhaps the greatest achievement of late 20th and early 21st century astrophysics is the arrival of a consensus model of the entire universe, lambda CDM cosmology. For countless generations of humans, we've marveled at questions such as, what is the universe? What makes it up? How far to the limits of what it's possible to observe does it go on for? How did it come into existence? And how long ago? How did it grow up to be the way it is today? And what will its ultimate fate be? Today, after unprecedented measurements of galaxies all throughout cosmic history, all sky imaging of the universe at microwave wavelengths, and thousands upon thousands of supernovae and other transient events all across the universe, we finally have our answers to these questions. Our universe, made of 68% dark energy, 27% dark matter, and just 5% normal stuff, began from a small, dense, nearly perfectly uniform state some 13.8 billion years ago in a hot Big Bang, and has been expanding, cooling, and gravitating ever since. At least, that's the consensus picture. But now, James Webb, along with its unprecedented infrared eye, has been rewriting what we thought we knew about the early universe. Instead of showing the formation of just a few small stars, which would satisfy the timeline of the hierarchical structure formation theory, the telescope is now sending back data that poses serious difficulties for the modern creation myth. As it looked deeper into space, the telescope revealed anomalies that challenged long-held prejudices about the origin and development of the universe, and shedded a brilliant light on profound and important scientific and philosophical questions. Indeed, you see, galaxies taken by James Webb had existed far before anyone had expected them to. In other words, somehow the universe is building galaxies earlier and faster than our theories predict. And this was no minor discrepancy. The finding is akin to parents and their children appearing in a story when the grandparents are still children themselves. Another way to imagine, it's like going to a nursery to visit your newborn and finding a room full of teenagers. And that's really disturbing, to say the least. So, what did this mean for the history of the universe? Frankly, Webb's discovery could have significant implications for cosmology, as it implies that current theories about the formation and evolution of galaxies could be incorrect or incomplete. To explain the existence of these galaxies, scientists may have to revise models of the universe's evolution and galaxy formation processes. One possibility is that these massive galaxies formed differently from the galaxies closer to us. For example, there may have been an unknown mechanism until now that allowed the formation of massive galaxies in a short period of time. Another possibility is that these galaxies are the result of exceptionally rapid mergers between smaller galaxies in the early universe, which would also require a revision of current models. In any case, the discovery made by the James Webb Space Telescope represents a significant advancement in the study of cosmic evolution and galaxy formation. This finding is likely to prompt astronomers to develop new theoretical models and seek more observational evidence to better understand the history of the universe and the properties of these enigmatic distant galaxies. But note that the impossible massive galaxies were not an isolated incident. Astronomers have long thought that newly minted galaxies that began merging together just after the Big Bang, about 13.7 billion years ago, were too fragile to boast any noticeable structures like spiral arms, bars, or rings. Those galactic features were thought to form during a time at least 6 billion years after the Big Bang. However, according to another remarkable study made by James Webb, these delicate shapes could have manifested as early as 3.7 billion years after the Big Bang, which is almost at the beginning of the universe. As Christopher Consolis, an astronomy professor at the University of Manchester in the UK, and a co-author of the new study, said in a statement, "Based on our results, astronomers must rethink our understanding of the formation of the first galaxies and how galaxy evolution occurred over the past 10 billion years." These findings come at the heels of another announcement presented by a different group of researchers, also based on Webb's data. which showed these early galaxies produced far fewer heavy elements than previously expected. However, the relationship between a galaxy's chemical composition and its evolution into a well-defined structure is not very well understood. Much of scientists' previous understanding on galaxy evolution came from data gathered by the Hubble Space Telescope, which is legendary in its own right, but still has only so much resolution. While Hubble's data showed early galaxies had irregular shapes, as was expected during galaxy mergers, higher resolution data from James Webb is peering deeper into the universe to reveal that those early galaxies actually had well-defined structures like our own Milky Way. The new findings were based on an analysis of 3,156 galaxies, which astronomers say is the biggest sample that has been studied thus far with Webb's data. In the words of Leonardo Ferreira, an astrophysicist at the University of Victoria in Canada and the lead author of the new study, for over 30 years, it was thought that these disk galaxies were rare in the early universe due to the common violent encounters that galaxies undergo. The fact that James Webb finds so many is another sign of the power of this instrument and that the structures of galaxies form earlier in the universe, much earlier in fact, than anyone had anticipated. According to the new study, the team classified the sample set of close to 4,000 galaxies from the early universe by shape, like disks, point sources, and spheroids. Team members further classified them as smooth or structured, with galaxies in the latter group featuring bursts of star formation and indications of mergers with other galaxies. Results showed that relatively well-defined structures in the universe form a lot quicker than previously thought, following what is known as the Hubble sequence, which is the standard classification of galaxies by their visual properties as ellipticals, lenticulars, and spirals. The latest findings suggest a need for new ideas that explain how galaxies evolved over the past 10 billion years. Elsewhere, there have been other Webb's occasions in which the evidence behind science's basic understanding of the universe has been found to be alarmingly inconsistent. Take the matter of how fast the universe is expanding. This is a foundational fact in cosmological science, the so-called Hubble constant. Yet scientists have not been able to settle on a number. There are two main ways to calculate it. One involves measurements of the early universe, such as the sort that the Webb is providing. The other involves measurements of nearby stars in the modern universe. Despite decades of effort, these two methods continue to yield different answers. At first, scientists expected this discrepancy to resolve as the data got better. But the problem has stubbornly persisted even as the data have gotten far more precise. And now, new data from the Webb have exacerbated the problem. This trend suggests a flaw in the model, not in the data. So, is it time to dethrone the Big Bang theory? Maybe. Like Dr. Luke A. Barnes, a postdoctoral researcher at Western Sydney University, said, "It's more likely that the story of the Big Bang will become part of a larger story." After all, Nicholas Copernicus's model of a sun-centric universe was never overthrown per se. Johannes Kepler simply refined the orbits of the planets, Isaac Newton explained the forces, and modern astronomy has placed our solar system in our galaxy and expanding space. We can only use observations and theory to peer so far back in time. So, for the Big Bang, there is plenty of room for a prequel, which explains what happened in the earliest fraction of a second of the life of the universe. Similarly, we can only see so far in space, to our cosmic horizon. The universe over the horizon could have the same properties as ours, or we could be part of a vast and variegated multiverse. But, as in the past, if you want to start a cosmic revolution, you've got to do it right. We all know that there are some problems with the Big Bang theory. Since scientists first proposed the Big Bang theory, many people have questioned and criticized the model. Here's a rundown on some of the most common criticisms of the Big Bang theory. First, it violates the first law of thermodynamics, which says you can't create or destroy matter or energy. Critics claim that the Big Bang theory suggests the universe began out of nothing. Proponents of the Big Bang Theory say that such criticism is unwarranted for two reasons. The first is that the Big Bang doesn't address the creation of the universe, but rather the evolution of it. The other reason is that since the laws of science break down as you approach the creation of the universe, there's no reason to believe the first law of thermodynamics would apply. Second, some critics say that the formation of stars and galaxies violates the law of entropy, which suggests systems of change become less organized over time. But if you view the early universe as completely homogeneous and isotropic, then the current universe shows signs of obeying the law of entropy. Third, some astrophysicists and cosmologists argue that scientists have misinterpreted evidence like the redshift of celestial bodies and the cosmic microwave background radiation. Some cite the absence of exotic cosmic bodies that should have been the product of the Big Bang, according to the theory. Fourth, the early inflationary period of the Big Bang appears to violate the rule that nothing can travel faster than the speed of light. Proponents have a few different responses to this criticism. One is that at the start of the Big Bang, the theory of relativity didn't apply. As a result, there was no issue with traveling faster than the speed of light. Another related response is that space itself can expand faster than the speed of light, as space falls outside the domain of the theory of gravity. There are several alternative models that attempt to explain the development of the universe, though none of them have as wide an acceptance as the Big Bang theory. For instance, the steady-state model of the universe suggests the universe always had and will always have the same density. The theory reconciles the apparent evidence that the universe is expanding by suggesting that the universe generates matter at a rate proportionate to the universe's rate of expansion. The ekpyrotic model suggests our universe is the result of a collision of two three-dimensional worlds on a hidden fourth dimension. It doesn't conflict with the Big Bang theory completely, as after a certain amount of time it aligns with the events described in the Big Bang theory. The Big Bounce theory suggests our universe is one of a series of universes that first expand, then contract again. The cycle repeats after several billion years. Plasma cosmology attempts to describe the universe in terms of the electrodynamic properties of the universe. Plasma is an ionized gas, which means it's a gas with free roaming electrons that can conduct electricity. There are several other models as well. Could one of these theories, or other ones we haven't even thought of, one day replace the Big Bang theory as the accepted model of the universe? To be honest, it's possible. As time passes and our capability to study the universe increases, we'll be able to make more accurate models of how the universe developed. However, you also need to remember that the Big Bang theory has a solid track record of explaining well-established facts about the universe. So, if you or any challenger want to challenge the Big Bang theory, you'd better be able to explain the basics before you have a shot at explaining mysteries like dark matter. Otherwise, notice that science isn't perfect, and that the Big Bang theory's journey from crackpot idea to accepted science has been long and messy and isn't over yet. According to scientists, if we know the Big Bang to mean the idea that the universe started out in a smooth, hot, dense state that was set into expansion, which led to evolution of structure, then no, the Big Bang has not been disproven. Either way, to be a successful theory of cosmic evolution, the Big Bang must explain all aspects of how we got from back then to now. How did that transition occur? When and how did the cosmos start to form all the structures we see today? When did the first stars form? And when did the first galaxies form? Using ever more powerful supercomputers to simulate cosmic history and ever bigger telescopes to test the results of those simulations, researchers have developed a remarkably complete story. If anything, it's proven the most basic feature of the theory: cosmic evolution. Thus, instead of overthrowing the Big Bang theory, many scientists strongly believe that this theory just needs some new updates. And the results of James Webb just reinforce the idea that the universe does have a story, and most importantly, we are somehow learning to tell it. For instance, In a recent groundbreaking discovery, the James Webb Space Telescope has observed light from stars surrounding some of the earlier supermassive black holes in the universe. Black holes seen as they were less than 1 billion years after the Big Bang. The observations conducted by a team from the Massachusetts Institute of Technology, or MIT, addresses the question of how these cosmic titans that sit at the hearts of galaxies grew to tremendous masses, equivalent to millions, sometimes even billions, of suns. More specifically, how did they grow so rapidly? And Webb's findings could also answer the riddle. What came first, the galaxy or the supermassive black hole? The supermassive black holes observed by the MIT team are insatiably feeding on surrounding material, generating immense tidal forces in a disk of matter called an accretion disk, thereby causing the disk itself to glow. This feeding situation powers objects called quasars, which sits at the hearts of active galaxies. Quasars are among the most luminous objects in the cosmos, with some so bright they outshine the combined light of every star in the galaxies around them. Supermassive black holes are surrounded by mystery too, especially when seen earlier than 1 billion years in the 13.8 billion year history of the universe. That is because the continuous merger process of black holes, by which scientists think supermassive black holes grow over time, should take many billions of years to proceed. So how could these giant voids exist only about 1 billion years after the Big Bang? Well, one suggestion is that they got a head start, forming from so-called heavy seed black holes. By using James Webb to observe faint light coming from stars in the host galaxies of 6 ancient quasars, for the first time, we collected evidence that supermassive black holes in the early universe indeed grew from heavy seeds. As Anna Christina Eilers, team member and assistant professor of physics at MIT, said in a statement, "These black holes are billions of times more massive than the Sun, at a time when the universe is still in its infancy. Our results imply that in the early universe, supermassive black holes might have gained their mass before their host galaxies did, and the initial black hole seeds could have been more massive than today." Discovered in the 1960s, the intense brightness of quasars was initially believed to originate from a single, star-like point. This led to the name quasar, which is a portmanteau of the term quasi-stellar object. Researchers soon found, however, that quasars are actually caused by vast amounts of matter getting accreted to supermassive black holes at the hearts of galaxies. However, these objects are also surrounded by stars, which are much fainter and more difficult to observe. That is because this stellar light is washed out by the brighter light of the quasar, the star's orbit. Thus, separating out light from quasars and light from stars around them is no mean feat, akin to seeing the light of fireflies sitting on the lamp of a lighthouse around a mile away. James Webb's ability to peer further back in time than any prior telescope, coupled with its high sensitivity and resolution, has made this challenge less daunting, however. Thus, the MIT team managed to observe light that has been traveling to Earth for around 13 billion years from 6 quasars in ancient galaxies. As team member Minghao Yue, a postdoc at MIT's Kavli Institute for Astrophysics and Space Research, said, "The quasar outshines its host galaxy by orders of magnitude, and previous images were not sharp enough to distinguish what the host galaxy with all its stars looks like. Now, for the first time, we are able to reveal the light from these stars by very carefully modeling James Webb's much sharper images of those quasars." The data obtained by James Webb included measurements of each of the 6 quasars' light emissions across a range of wavelengths. This information was then introduced to a computer model detailing how much of this light could be attributed to a compact point source, the accretion disk around the black hole, and how much can be attributed to a more diffuse source, the stars scattered around the galaxy. By splitting the light into 2 sources, the team was also able to infer the mass of both elements of these galaxies. This revealed that the supermassive black holes have masses equal to around 10% of the masses of the stars around them. While this might sound like a massive imbalance in favor of the stars, consider how in modern galaxies, central supermassive black holes have masses merely 0.1% that of the stars in their surrounding galaxies. This tells us something about what grows first. Is it the black hole that grows first, and then the galaxy catches up? Or is it the galaxy and its stars that first grow, and they dominate and regulate the black hole's growth? We see that black holes in the early universe seem to be growing faster than their host galaxies. That is tentative evidence that the initial black hole seeds could have been more massive back then. As Yue concluded, after the universe came into existence, there were seed black holes that then consumed material and grew in a very short time. One of the big questions is to understand how those monster black holes could grow so big, so fast. There must have been some mechanism to make a black hole gain their mass earlier than their host galaxy in those first billion years. It's kind of the first evidence we see for this, which is exciting. In another brand new study, astronomers, by use the Webb telescope, has just discovered that a scorching hot lava planet, believed to be composed of diamond, grew a second atmosphere. And that was after its star destroyed its first atmosphere. The planet, known as 55 Cancri E, is located around 41 light-years from the solar system and has a width almost twice that of Earth and a mass around 9 times greater than our planet. Among the bucket of extrasolar planets, or exoplanets, scientists have cataloged over the years, this world is classified as a super-Earth. That means it's more massive than Earth, but way lighter than planets like Neptune and Uranus. Still, that's where comparisons to our world end for 55 Cancri A. This exoplanet is so dense that astronomers have hypothesized it to be composed of mostly carbon that's been compressed to diamond. Also, the exoplanet exists a mere 2.3 million kilometers from its sun-like star, 55 Cancri A. That's equal to 0.01544 times the distance between Earth and the Sun. This proximity means 55 Cancri E orbits its host star once every approximately 17 Earth hours, and has a roasting hot surface temperature of around about 2,400 degrees Celsius. The radiation from its star has thus stripped 55 Cancri E of its original or primary atmosphere, just as is seen with other rocky planets that orbit their stars at such close proximities. However, the new research indicates a thick layer of gases surrounds the planet, implying it has grown a second atmosphere. And the scientists behind the discovery thinks they know how this happened. As Renyu Hu, a member of the team behind this discovery and a researcher at the California Institute of Technology, or Caltech, said, "We measured the thermal emissions from this rocky planet, and the measurement indicates that the planet has a substantial atmosphere. This atmosphere is probably supported by outgassing from the rocky interior of 55 Cancri E, and we think this is the first measurement of a secondary atmosphere on a rocky exoplanet. It is very exciting." 55. Cancri E was found in 2004 by the wobble it caused in its host star's motion, as seen from our perspective on Earth. This is called the radial velocity exoplanet discovery method for exoplanet discovery. Originally named Janssen, the world was the first super-Earth identified orbiting a distant main sequence star, or a star that is still converting hydrogen to helium at its core. As the planet was investigated further, scientists also learned about its 0.7 Earth-day orbit and carbon composition. Then, in 2016, the Hubble Space Telescope determined that the atmosphere of 55 Cancri A contained hydrogen and helium during what was the first atmospheric investigation of an exoplanet. 2 possible scenarios exist to explain the atmosphere of 55 Cancri E. First, the super-Earth could be a lava world atop which a thin, vaporized silicate atmosphere exists. It'd be made of the planet's volatiles and chemical compounds like carbon, nitrogen, hydrogen, and sulfur that can be easily lost due to irradiation from its star. Or, alternatively, the planet could have a thick secondary atmosphere created over time through volcanism. To investigate which of these scenarios was correct, Hu and colleagues examined Webb observations of the planet as it passed behind the star 55 Cancri A, an event called a secondary eclipse. Data from 2 secondary eclipses of 55 Cancri E ruled out the possibility of it being a virtually bare lava world, lacking a substantial atmosphere. There is no doubt that the planet is a lava-coated hellscape, and the team even thinks it is this molten nature that helped 55 Cancri A grow its secondary atmosphere. 55 Cancri E is so close to the host star that it receives a lot of heat in the form of radiation. That heat keeps the temperature on the planet very high, Hu said. At these temperatures, everything on the planet is molten. If it's rock, it's molten lava, which helps the outgassing process that supports a secondary atmosphere because of a molten surface. He explained that gas dissolves in 55 Cancri's global lava ocean, constantly bubbling out to form the secondary atmosphere. The researcher added that the original atmosphere of 55 Cancri E, which it would have had since its formation around its star, would have been composed of mostly hydrogen and helium. However, the composition of the secondary atmosphere that replaced the first remains uncertain. The composition of the secondary atmosphere depends on what the rock beneath it is made of. If the rock is very reducing, made of compounds that gain electrons and hydrogen, it can also create a hydrogen-helium atmosphere like the primary atmosphere. But if the rock is more like Earth's mantle, water, carbon monoxide, and carbon dioxide would dominate the secondary atmosphere. While James Webb's observations of 55 Cancri E don't conclusively say what the planet's atmosphere is composed of, models used to explain the measurements favor a substantial amount of carbon dioxide and carbon monoxide. On the other hand, note that 55 Cancri E is by no means the only rocky planet seen orbiting so utterly close to its host star, though Hu points out it is among the hottest of its kind. So, does this mean that these other scorching hot terrestrial worlds could have grown secondary atmospheres too? Well, the team isn't sure. That's because there is something fairly unique about 55 Cancri A. At 1.8 times the size of Earth, it's a fairly large chunk of rock, and that helps to retain the volatiles against stellar irradiation. We expect a very small rocky planet that is in a very close orbit around its star could lose its entire volatile budget from the whole planet, and then it becomes atmosphere-less. That means it's not just the distance between a planet and its star that determines whether a planet will retain its atmosphere and grow another, but also the size of that world. So, on both counts, 55 Cancri E seems to be optimized for replacing a lost primary atmosphere with a secondary atmosphere. The analysis of 55 Cancri E in this way would have been impossible without the observing power and infrared sensitivity of the James Webb Telescope, which makes it ideal for characterizing the atmospheres of exoplanets. Scientists now are definitely thinking about the next steps for studying 55 Cancri E. They have some ideas about making the measurements of the planet's thermal emission, not just during secondary eclipses, but also as the planet revolves around the star. This will tell us about the size of the atmosphere and circulation within. That's all the information that we have for you today. Don't forget to give us a thumbs up if you enjoyed today's episode, subscribe if you haven't already, and hit the bell so you never miss out on future episodes. And be sure to also tell us what you think about today's content. Everyone's support motivates us to continue delivering quality content and to always improve. As always, thanks for watching, and we will see you next time.